the chemistry lesson video for section 14.3. So if you watch 14.2, we learned Boyle's law, Charles' law, combined gas law, Gay-Lussac's law. And so in 14.3, we're going to focus on ideal gas law. Now, a lot of people struggle with ideal gas law because everything has to have a particular unit. And so sometimes there's a lot of converting, and sometimes there's not. But sometimes there is, and we know that some of you struggle with converting. So just be prepared. If you need converting help, go all the way back to chapter 3, because we've been doing it since then. All right, so the ideal gas law allows us to calculate volume, pressure, temperature, or number of moles of gas. And then notice the other difference in the formulas from section 2 is that they had 1s and 2s, and these are all there's just one of each variable. So P is pressure, but now it has to be in kilopascals. Now, if you're using like Boyle's law or Gay-Lussac's law or combined gas law, it can be in any unit as long as if you have two of them, they're the same unit. But in ideal gas law, it has to be in kilopascals. Volume has to be in liters for ideal gas law. Again, if you're talking about Boyle's law, you can have milliliters, that's fine as long as they cancel if you have two. Now our new variable is N. N is number of moles, and so it of course needs to be in moles. So if I give you grams, you're going to have to use molar mass to convert to moles, like we did back in stoichiometry. All right, R is our other new variable. Well, it's not a variable, it's a constant, but our other new letter. And it is the ideal gas constant, and so it will always be 8.31 liters times kilopascals over moles times Kelvin. Now, the only reason it has this extensive list of units behind it is so that everything will cancel out and you'll be left with one unit at the end. I will have the formula on your formula sheet, but I will not have the 8.31, so make sure you know the gas constant. And then last is temperature, and just like in the other gas laws, it has to be in Kelvin. So you'll add 273 to get it to Kelvin. All right, so let's just go ahead and dive in, and like I said, sometimes you need to convert, sometimes you don't. So I gave you a variety of ones for us to go through together. So here's our first one. So it says a deep underground cavern contains 2.24 times 10 to the 6th liters of methane gas. So that is my volume. And for ideal gas law, volume does have to be in liters. So that one's okay to stay as is. Of methane gas at CH4, which is CH4, at a pressure of 1.50 times 10 to the 3 kPa. So that's my pressure. And then for ideal gas, pressure does need to be in kPa, so that number is fine the way it is. And a temperature of 315 Kelvin. So there's my temperature, and it's in Kelvin, which is exactly what I want. But here's where the trick comes. Then it says, how many grams of CH4 does the cavern contain? So we're looking for grams of CH4. Well, our formula is PV equals nRT. So we have pressure, volume, number of moles, a gas constant, and temperature. So which one of those could be turned into grams? The moles. Okay, so what we're actually going to do is we're going to solve for N and then turn that into grams. Okay, so in ideal gas law, if they ask you about grams, you just always start by solving for moles because we can always use molar mass to change to grams. Okay, so once I realize I'm solving for N, I need to rearrange my formula. So I need N to be alone, so I divide both sides by R and T. So they cancel on that side, so N is P times V over R times T. And so since I've labeled everything as I always do, it's super easy to plug in. So my pressure is 1.50 times 10 to the 3 kPa. My volume is 2.24 times 10 to the 6th liters over my R value. And notice they're not going to discuss R in the problem at all. You need to know it in your mind. It's 8.31 liters times kilopascals over moles times Kelvin. And remember, you're not plugging things into this. These are just the units. It's kind of like if I said you're driving 50 miles per hour. There's 2 units there. This just happens to have 4 units. And it's just so everything will cancel all nice and neat at the end, which I'll show you in a second. So R times T, which our temperature is 315 Kelvin. So now let's look at why R has these complex units. Well, if you look, kilopascals cancels out. Liters cancels out. Kelvin cancels out. and we are left with moles. So that's why R has those complex units. It's just so everything cancels. Now, hopefully you remember from section 14.2 video, you multiply the top, then hit divide, and then put the bottom in parentheses so you can put multiply in the middle. Okay, important thing is make sure you're getting the right answers that I'm getting for these. Setting it up is one thing, getting the right answer is the other part. All right, so once you solve for this, I ended up getting 1.28 times 10 to the 6 moles. So I have moles as my answer, but what's the problem? The problem is it didn't want moles as my answer, it wanted grams as my answer. Okay, so now I'm going to need to convert. So like I said, for ideal gas law, because every single thing has a specific unit, you just really have to watch your conversions. Okay, so I'm going to bring this down here just so I have a little more room. So I have 1.28 times 10 to the 6 moles, and it told me we're talking about CH4. So if you remember all the way back to stoichiometry, we change moles to grams by using molar mass. So I find C on the periodic table is 12, H is 1 times 4, so it's 16 grams in 1 mole. I follow my golden rule and put mole on bottom. And so how many moles? Well, molar mass always equals 1 mole. And then I put my 16 grams on top. And remember, molar mass, y'all, just comes from the numbers I add up off the periodic table. So I just do my 1.28 times 10 to the 6 times 16, and I end up getting 2.05 times 10 to the 7 grams of CH4. Just like that. Okay, so in this one, pressure was in the right unit, volume was in the right unit, temperature was in the right unit. The only thing I had to do was I had to change moles to grams. So you have to remember, in ideal gas law, if you see grams, you can always go between grams and moles as long as they tell you the formula or the molar mass. All right, so let's look at another one. And so remember, sometimes there's converting, sometimes there's not. It just depends on the question. All right, so maybe pause the video and try this top one, because this top one doesn't have any converting. So this is a good one for you to start with. Okay, I'll assume you've done that already. So it says, when the temperature of a rigid hollow sphere containing 685 liters of helium, so that's my volume, and liters is the correct unit, is held at 621 Kelvin. So there's my temperature, and Kelvin is the correct unit. The pressure of the gas is 1.89 times 10 to the 3 kilopascals. So there's my pressure, and kPa is the correct unit. How many moles of helium, so that means I'm looking for N, does the sphere contain? And N is moles. So in this case, I don't have to convert at all. See, that's the problem that some of y'all have, is you assume once I show you how to convert for ideal gas law, you always have to convert. You don't. It just depends on the question. So P times V equals N times R times T. And so here I'm solving for N again. So to get it by itself, I'm going to divide both sides by R and T. And so on that side they cancel. So N equals PV over RT. So then I'm just ready to plug in. So my pressure is 1.89 times 10 to the 3 kilopascals. My volume is 685 liters. My R value, which again is not going to say anything about the R value in the problem. You have to know it in your mind, 8.31. And it's liters times kilopascals over moles times Kelvin, times my temperature, which is 621 Kelvin. So remember, the R value just has those complex units, so they all cancel. So if you see, kilopascals cancel, liters cancel, Kelvin cancels, so I'm left with moles. So I just do 1.89 times 10 to the 3 times 685 divided by parentheses 8.31 times 621 close parentheses. And once you do all that, you should end up getting something like 250.9 moles. Okay? And here it didn't tell, oh, it did tell us of helium. Sometimes it doesn't tell you the gas, so I'm not super picky about whether you put the substance in the gas laws, because a lot of times it'll just say a gas. All right, so hopefully you got that one right. Now if you're feeling super confident in your ability to convert, you can try this bottom one. I'll go ahead and tell you, you have to convert everything. All right, I'm just trying to show you the easiest possible example, the hardest possible example, and then the previous one we did was somewhere in the middle where we just had to convert one thing. Okay, so if you want to try this one, you can. Otherwise, if you're not feeling good at converting, just watch me do this one. So it says a child's lungs can hold 2,200 milliliters. That is a volume, but the problem is in ideal gas law, I have to have it in liters. So to go from milliliters to liters, you just divide by 1,000, or you can move your decimal 3 places to the left. So it becomes 2.2 liters, okay? Because hopefully at this point you all know that there's 1,000 milliliters in a liter. All right, so you just take 2,200 and divide it by 1,000. That's all you have to do. All right, it says how many grams. So remember, what did I tell you solve for if you're looking for grams? You solve for moles first, and then you can change it to grams. How many grams of air do her lungs hold at a pressure of 1.007 atm? So there's my pressure, but remember, for ideal gas law, pressure has to be in kPa. All right, so to save room over here for me to work the problem, I'm going to convert over here. So we have 1.007 atm. So remember, golden rule says whatever I have on top goes on bottom. So if you look at your conversion factor, it will tell you 1 atm equals 101.3 kPa. Okay, and that's just from that big conversion factor that says 1 atm equals 760 millimeters of mercury equals 101.3 kPa equals 760 torr. So you just do 1.007 times 101.3 and divide by 1. And for that, you end up getting, let's see, where's my answer here? 102 kPa. All right, so I'm going to use 102 kPa instead of the atm. And a body temperature of 37 degrees Celsius. Well, that's temperature, but we know we can't use Celsius, so 37 plus 273 ends up being 310 Kelvin. All right, so then because they told me air doesn't have a molecular formula because it's a mixture of gases, so they told us the molar mass that we can use. So we'll use this when we need to convert our moles to grams. All right, so we're solving for N again. Remember, you don't have to solve for N. I just obviously happen to pick 3 where we're solving for moles. You can solve for any variable. I mean, obviously you probably wouldn't solve for R because we already know what that is. So I get N by itself by dividing both sides by R and T. So P times V over R times T again. And so I just plug in. So I changed my pressure to 102 kPa. I changed my volume to 2.2 liters. My R value is always 8.31 liters times kilopascals over moles times Kelvin. And my temperature, I changed to 310 Kelvin. So again, my kilopascals cancel, my liters cancel, my Kelvin cancels, and I'm left with moles. So once I multiply on the top and divide by the bottom, I end up getting 0.087 moles. But the problem is they want grams. Now again, air does not have a molecular formula because it's a mixture, but they gave me the molar mass, 29 grams per mole. So I want mole on bottom because of course my golden rule, and they told me it has a mass of 29 grams on top. So I just do 0.087 times 29 and I end up getting about 2.5 grams. And you can put up air if you want to. Again, it doesn't matter because a lot of times they won't tell you what the gas is that we're talking about. Okay, so this was an example where we didn't have to convert it all. This was an example where we had to convert everything, and the previous one was an example where we just had to convert one thing. So ideal gas law, it doesn't always involve converting, but you just do have to be careful to check to see if you need to. So I'll go ahead and tell you, throughout all my years of teaching, my students struggle most with this one because of the converting. And because they see grams and moles and freak out and have flashbacks from the most awesome chapter ever, stoichiometry. So let's move on. So ideal versus real gases. So this is called the ideal gas law. As we know, ideal means something that's perfect, and that doesn't happen in real life. So what's the difference? What does ideal mean? So an ideal gas follows rules that scientists have created and remains a gas at any temperature and pressure. These do not exist. So in reality, if I have a gas, if I cool the temperature down enough or apply enough pressure, I can turn it into a liquid or a solid. But when we're talking about an ideal gas, we assume it never changes state because then that would make our calculations not work correctly. A real gas changes to a liquid or solid at low temperatures and high pressures. So why do we use ideal gas law if it's not the real answer? Well, at certain temperatures and pressures, it's close enough to the real answer, and the calculations are very easy. As much as some of you just hated that one where I had to convert everything, that is considered considered a super easy calculation when you compare that to what you do in advanced chemistry. That's like the basic, easiest thing that I can even come up with. Okay, so if you hated that, then if you're going to go into advanced, up in physical chemistry and all that kind of stuff, then just get prepared. Okay, so we make this assumption because it makes our calculations easier. We can just use basic algebra instead of going into calculus and that type of thing. So real gases differ most from ideal gases at low temperatures and high pressures because real gases turn into liquids and solids. And so obviously a liquid or a solid is not going to act like a gas. The particles are very different at that point. So, section assessment. Under what conditions do real gases deviate most from ideal behavior? So it's when are real gases the least like ideal gases? Well, it's at low temperatures and high pressures because real gases become liquids and solids. Number 2, what is an ideal gas? An ideal gas follows the rules that scientists have created and remains a gas at all temperatures and pressures. Okay? A real gas follows the rules scientists have created and remains a gas at all temperatures and pressures. Alright, so here's 2 more to try. These don't have nearly as many conversions. Actually, if I glance at them, I don't think they barely have any except maybe temperature. So these would be 2 good ones for you to try, especially if you're getting nervous about that last one where I had to convert everything. Alright, so maybe pause the video and try 3 and 4, or watch me do 3 and then you try 4. But just make sure you try these. So it says determine the volume, so I know I'm looking for V, occupied by 0.582 moles, so that's N, of a gas at 15 degrees Celsius. So that's my temperature, but of course I need it to be in Kelvin, so I have to add 273. So once I do that, I get 288 Kelvin. If the pressure is 81.8 kilopascals, so there's my pressure, and kilopascals is appropriate for ideal gas. Alright, so on this one, all I had to convert was temperature. So see, every ideal gas problem is not only converting. So we know PV equals nRT. Here I'm solving for V. So to get it by itself, I divide both sides by P. So V equals nRT divided by P. And then because I've labeled everything, I just plug in. So my N is 0.582 moles. My R, of course, is my ideal gas constant, which is 8.31 liters times kilopascals over moles times Kelvin. My temperature is 288 Kelvin. And my pressure is 81.8 kilopascals. So if you look, my moles cancel, my Kelvin cancels, my kilopascals cancel, and I'm left with liters. So then I just multiply across the top and divide by 81.8, and I end up getting about 17 liters. And that's it. So see, they aren't all that hard. And if anything, then you don't have to worry about the 1s and 2s and mixing them up. Alright, so number 4, if you haven't tried it, pause it and try this one, and we'll look at it together. So it says, what pressure, so I'm looking for P, is exerted by 0.45 moles, so that's my N, and it's in the correct unit, of a gas at 25 degrees Celsius, so there's my temperature, but of course I need to add 273, so it becomes 298 Kelvin, if the gas is in a 0.65 liter container, so there is my volume. Alright, so this time everything was in the correct unit except temperature, so I fixed that, so now I'm ready to plug in. So PV equals nRT, this time I'm solving for P, so to get it by itself, I divide both sides by V. So P equals nRT divided by V. And so now that I've labeled everything, I'm just going to plug in. So my N is 0.45 moles. My R is my constant, 8.31 liters times kilopascals over moles times Kelvin. My temperature I changed to 298 Kelvin. And the whole thing over my volume, which is 0.65 liters. So my moles cancel. My Kelvin cancels, my liters cancel, I'm left with kilopascals. So I multiply across the top and divide by my 0.65, and when I do that, I get 1,714, and my unit is kPa because I'm solving for pressure. Alright, so like I said, don't let ideal gas law scare you just because it can have a lot of converting. It doesn't have to. Okay, and so you know you use ideal gas law when you only see one volume, one temperature, one pressure, instead of seeing 2 like you would in Boyle's, Charles, Gay-Lussac's, or combined gas law. Alright, so hopefully again, you're not getting overwhelmed by our amount of formulas. Remember, don't memorize the formulas. They're going to be on your formula sheets.